Right, in this simulation we have two metallic heads. Actually, this one's copper and this one's even better conductor, but I don't think that makes much difference. We have a vertical dipole radiating waves that are being absorbed on the boundary by some Muir boundary conditions. We can see that on the inside there's some, obviously no waves can penetrate this region here, and obviously here as well the waves can't penetrate. We can see the other different field components that are being generated in X and Z and then in Y. Well, this simulation is about 326 by 230 by 166 cells. That's about 12 megacells, and we're getting about 1,340 megacells per second. In actual fact, and it's being carried on a GTX Titan. In actual fact, it's been almost in no way optimized, and it's using the full set of coefficients. So if we imagine each cell has actually got 12 coefficients for the 6 field components, and it's having to read that in for this 12 million cells, and we're getting an update rate that's pretty quick. Okay. Right, here we have the same model with two heads, exactly the same space as before, 326 by 230 by 166, about 12 megacells. We're getting about 1340 megacells per second, and we see here the field that's normal to the surface of these conducting heads. Let's just increase my speed of navigation. You can see it gives you an idea of just how many triangles are being updated as the FDT calculations are taking place. So, as I said, this is being carried out on a GTX Titan. It has plenty of memory, and we're probably using only 20% of the memory. It's a very inefficient version of the software because at the moment we're actually reading in 12 coefficients for each FDTD cell, and there's 12 million of those. So the fact that we're getting such good speed is actually very good news, because hopefully this will go much faster. And we can see the field on the inside, or as seen from the inside. If I change over, and I can see the different field components. There's the total field. We would expect this to be pretty symmetrical because the dipole is actually in the center, between the heads equally spaced. We can see different color schemes. So I put this color scheme here, which is this one, which is 16 leveled, I think. This one, which is very fluorescent. And this one, which is another 16 level one, I think. This one here, where the green isn't being used. We can change the field components. The green isn't being used here, it's just the red and the blue. By the way, red is positive field and blue is negative field. We're obviously watching the field in time as time progresses, and the field is a real quantity which can be either positive or negative. These are the different field components. Back onto the normal field, I think. I can change the dB scale so we can see more or less effect. I can also change the reference level so we can see that where the field is strongest in the zone here becomes white. So this is a case of using the GTX cards to visualize electromagnetic fields. Oh,